It's probably important. Should always check that. I gave answers to the previous problem. I wrote those on the board. We're going to be moving on now into Karnaugh Maps. That's pronounced Karnaugh. We did an example. I wrote out the truth table. And now we're going to be talking about gray code. So here with gray code, regular binary is represented as like 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, etc. Okay? So we can count that way with regular binary. However, this does pose an interesting challenge because you'll have multiple digits switching simultaneously. So, for example, oh, really? Oh, dang. Well, it means I can only write to like right here. All right, whatever. So, regular binary is represented as all of these numbers. Oh, that's true. I could just move it. That's thinking like an engineer. There we go. Okay, this poses an issue with multiple digits switching simultaneously, such as to go from 7 to 8, you have 1, 1, 1 to 1, 0, 0, 0. Or 0, 1, 1, 1 to 1, 0, 0, 0. Okay? You have 4 digits changing. Which means you have to correctly capture the change in all 4 of those numbers simultaneously, because if you don't,
Olga just said much better now that I hear that sexy voice.
oh man. If you don't capture all 4 digits changing simultaneously, all right, let's say you measure your system right at a time change, and during that time change, some values have not yet changed. They may be instantaneously too soon. You may be reading 0110, you may be reading 0100, meaning both of these numbers have changed. This one has not, this one has not. You may be reading this number. You may be reading this number. In fact, you may be reading any number between 0 and 15. If you don't measure them all at the same time, this can pose serious issues, because now when you measure what these 4 values are at some instant in time, if they have not all changed yet, and if you do not know whether or not they have all changed, your measurement could be off by 7 numbers, both direct. You have no idea what the number actually is. So this poses a huge problem. Okay? Now, computing is fast enough in today's world that this isn't as big of an issue. But there are still sensor systems that do rely on gray code because, for example, let's say I'm spinning a wheel. Okay? And as I spin this wheel is divided into 15 different pizza slices, right? And this one here will be 0, 0, 0, 0. This will be 0, 0, 0, 1, 0, 0, 0, no, 0, 0, 1, 0, and so on and so forth, all the way around this circle. Okay? When I go to read a number, if I read right on this line, between 0, 0, 0, 0 and 1, 1, 1, 1, I may get some of those digits wrong. Just because even off by a millimeter both ways, they're not all reading the same thing. So gray code is the solution. Okay? Gray code is the solution to this because in gray code, the way that you count, you only change one number at a time. All right, so here, just using two numbers as an example, we go 0, 0 to 0, 1 to 1, 1 to 1, 0 back to 0, 0. All right, so if I had a circle that had 4 partitions to it, 0, 0, 0, 1, 1, 1, 1, 0, if I land right on this line, I will be either measuring 1, 0 or 0, 0, which are the two numbers that it's right next to. That's great. I either end up with this number or this number when I take that measurement. Similarly, if I take a measurement at that position, and I've got my voltage versus time chart, and here I've got, it changes here. So that'll be, that'll represent, no, I'm going to use blue and red. It's because I never use colors in my lectures. And I should. So let's say right here, we have it changed from 0 to 1. But right here, it stays at 0. Okay, so over here, this is 0, 0. Over here, this is 1, 0. If we take a measurement right here, we do not know whether we're going to be reading 1, 0 or 0, 0. Now the nice piece about that is, if I read 1, 0, that's just the previous state. It doesn't change that much. If I read 0, 0, it's just the next state. So I'm either reading the previous or the next, depending on which value my 1 becomes. Okay? So does that make sense why gray code has some merit to it? Really only shows up in counting situations, but it's still valuable when it comes to counting. And there are probably some applications of that too, but whatever. Any questions on gray code? Let me try to represent more than 3 digits in gray code. No, I want to because I don't think I've ever written that out in class before. So here, it shows it off in 3 digits. Oh, here's 4-digit gray code. So here you have 0, 0, 0, 0, and that represents 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes, I am just counting to 15. Nice. Well done, Kale. I'm going to go ahead and do a separation between each two. Oh. So this is 0, 0, 0, 0. And really I have to look this up because I don't have this all memorized. 0, 0, 0, 1. 0, 0, 1, 1. 0, 0, 1, 0. 0, 1, 1, 0. 0, 1, 1, 1. 1, 1, 1. I think that, nope, I didn't do that right. That's 1, 0, 1. So 0, 1, 0, 1. 0, 1, 0, 0. 1 1 0 0, 1 1 0 1, 1 1 1 1, 1 1 1 0, 1 0 1 0, 1 0 1 1, 1 0 0 1, and then 1 0 0 0. Nice. And what you'll notice out of this gray code is that these digits are always just continuously repeating the 4 digits that you have. Continuously and always. Meanwhile, these 4, all of them are zeros. All of these are 0 1s. These 4 are all 1 1s. These 4 are all 1 zeros. Okay? In this column, all of these are 1s. Down here, all of them are zeros at the top. In this one, it's 4 zeros, 4 1s, 4 1s, 4 zeros. Here, it's 2 zeros, 2 1s, 2 1s, 2 zeros, 2 zeros, 2 1s, 2 1s, 2 zeros. And then this one just oscillates every time. Okay? So, I'm not going to teach you mnemonics of how to remember that. You can look up a table online. All right, so now with this as a foundation, now that we understand a little bit of gray code, how to write it, whatever, all that fun stuff, I'm going to create what's called a Karnaugh map. A Karnaugh map is a truth table that is a little different. On this top, I'm going to have A1. On this bottom, I'm going to have A2. There's only 4 entries in my truth table, so there's only going to be 4 boxes to this Karnaugh map. And I'm going to represent this as 0 and a 1. And I'm going to represent this as also as a 0 and a 1. Okay, and now I'm going to go in and fill in where my 1s are for my truth table. So here, I have a 1 that occurs at 0, 1. So here, A1 is equal to 0, A2 is equal to 1. This is a 1. I also have a 1 that shows up at A1 is equal to 0, A2 is equal to 1. Well, no, the other way around. A1 is equal to 1, A2 is equal to 0. So I have 2 1s that show up here, like that. Okay? This is a Karnaugh map.
So you're just looking at your Q values?
Just looking at Q. You take a truth table, you take the outputs of it, and you only focus on Q. So yeah, you could do a Karnaugh map for each individual one of those outputs, but yeah, this is Q. It's a good question. Okay, well, this doesn't tell us a whole lot. But it exists. Now we're going to break it out and we're going to do a 4-input statement. Okay, but instead of giving you the circuit, so we've already worked through that today, I'm just going to give you the truth table. And then we're going to turn it into a Karnaugh map. Yeah. You can write the zeros in, but for a Karnaugh map, you actually don't have to. Because electrical engineers, you don't want to do more work than you have to. And plus, when you're dealing with like systems that have 8 variables in them, you stop caring about the what is 2 to the 8th? It's like 256. You stop caring about 256 squares. You only want to write in the ones. So we'll do 4 inputs. Okay, we'll have A1, A2, A3, A4 as inputs. We'll go ahead and write out our 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. 16. All right. Now I'm just going to give you this truth table rather than draw up a circuit for it. The assumption is if you really want some more experience with working through logic gates, there's a lot of resources in your textbook. And eventually I'm going to give you a reading assignment. Eventually. Oh, but not now. So I'm just going to give you a truth table here. There you go. Now I randomly gave you ones and zeros to fill out that truth table. I could build a circuit to showcase this, but at this point, you're kind of looking at these and going, I don't know how to make a circuit out of this. If this is the truth table you needed, I wouldn't expect any of you to know how to take this and produce something with it. That's next class. It's really not that bad. This is the foundations of how to take a truth table and turn it into a circuit, and an optimized circuit. All right, so let's turn this into a Karnaugh map. Now what we'll have here is, how many rows do we have in our truth table?
16.
We have 16. So we're going to have 16 different boxes in our Karnaugh map. Okay? Now, we could arrange this in a number of ways. We could have A4 here, and then A1, A2, A3 up here. That sucks. We could have A1, A2 up here, A3, A4 down here. If we did that, it would be a 4 by 4. If we did the 3 on top, 1 on the side, it would be an 8 by 2. You'd still end up with 16 squares. But then you could do A1, A2, A3, A4, and then it would be a 2 by 8 matrix. I just like the 4 by 4 because it seems a little cleaner to me. So I'm going to leave it as A1, A2, and then A3, A4 over here. And now what we'll do is we'll represent this as gray code. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Okay? We'll draw the boxes. And then up top, 0, 0, 0, 1, 1, 1, 1, 0. Okay, now once again, 0, 0 here represents A1, A2 being both off. All right? That would go here, 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 here. All 4 of those would be represented by A1, A2 being off. All 4 of those conditions are represented by A1, A2 being off, but then the other conditions are A3, A4 are off, which is this row, is this box. Here, A4 is on, A3 is off, so that would represent this row. Both of them are on, which would represent this row. And then A3 is on, A4 is off, which would represent that row. All right? So that is the 4 different outputs that you can have with A0, A1, A2 both being zeros. Does that make sense so far? We're just rewriting the truth table into matrix form. Now I'm only going to put in the ones, as I've said. Sometimes it's easier to put in the zeros, and then the idea is if you put in the zeros, you didn't put in the ones. So like if my matrix is, this is a 0, the assumption is everything else is a 1. Okay. So here we'll only put in the ones. We have this when A1, A2 is 0, both of these cases, but then if A3 and A4 here, so this is going to be 1 and 1. Here this is 0, 1, 0, 0, so 0, 1, 0, 0. Here this one is 0, 1, 1, 1. Here this one is 1, 0, 0, 1, so 1, 0, 0, 1. Here this is 1, 0, 1, 1. Here this is 1, 1, 0, 1. And then here this is 1, 1, 1, 0, 1, 1, 1, 0. And then lastly, 1, 1, 1, 1. You suffered through this already. You don't have to be here.
0, 1, 1, 0 is off.
Which one?
0, 1, 1, 0.
0, 1, 1, 0. This one?
No.
So, yeah, that should be off.
Never mind, I did it backwards.
You got to make sure you do gray code. And there's a reason why that's true.
So I can't do A1, A2 on the left and A3, A4 on the right.
Oh, you can, yeah. That's fine. What your table will be is just this, just flipped like that. That's fine. All right. So what you'll see here, and here's what I want to point out to you. This is true if all four of these are on. Every single condition where A3, A4 are on, it is true. 1, 1, 1, 1, 1, 1, 1, 1. Each time it's on, this is on. This is also true each time, this 4 box right here, every time A1 is on and A4 is on, this is true. So here, 101, 101, 1 and 1, 1 and 1. All 4 of those are ones. This is what the Karnaugh map shows. Any numbers that are adjacent actually represent a commonality. Here, these two numbers are adjacent. This number is by itself. It's not adjacent to this one, this one, this one, or this one, so it's kind of by itself. But other than that, most of these have other connections. We can use that to build circuits, which we'll be doing in the next class after our lab. So bring your Raspberry Pis. We'll be doing a lab in class on Thursday. Huh? I'll see you then. And I will be posting a homework assignment. So